Welcome to Spring LIB.
For this question, we're asked to design a double-slit apparatus where the central diffraction peak contains 17 fringes. Assume the first diffraction minimum occurs at an interference minimum for part A, and for part B, we're going to assume that it occurs at an interference maximum. Okay, so the central diffraction peak contains 17 fringes. So that is, there will be 8 fringes on either side of the center, right? The ninth interference maximum of the double slit must coincide with the first minimum of the diffraction pattern for the single slit. So I'll say that again. Since there are 17 fringes, that means there is 8 on either side of the center. The ninth interference maxima of the double slit experiment must coincide with the first minima of the diffraction pattern from the single slit. So for part A, the missing order of interference fringe is 9, and the condition for interference minimum is the distance between the slits, d, times the sine of the angle theta, is equal to m plus 1/2 times lambda. Where here, again, d is the distance between the slits, theta is the angle between the slits, lambda is the wavelength of light, and m is the integer for the number of interference that we're dealing with. In this case, we're dealing with 9 since the missing order of interference is fringe 9. So we can say m equals 9, and we're going to rearrange this equation to solve for the distance between the slits, d. So, to solve for sine theta in terms of lambda and d. So what we have here is sine theta is equal to, we have 9 plus 1/2, which is 9.5, times lambda divided by the distance between the slits, d. The condition for a minima in a single slit diffraction, so if we have a single slit diffraction, the condition for a minima, we use capital D for the distance, times the sine of the angle theta, is equal to, in this case, it's just m times lambda. Well, we already found an expression for the sine of the angle theta. We found that above, so we could replace that here. And again, d is the distance between the slit and the screen. Theta is the angle, lambda is the wavelength, and m is an integer. But for the minimum of a single slit diffraction, m here is equal to 1. So we can go ahead and simplify this a little bit by plugging in m equals to 1. So we'll just maybe write that off to the side here. We can say m equals 1. Rearranging this, we find that d times 9.5. So I'm replacing sine theta here with 9.5 lambda over little d is equal to lambda when I replace m with 1. Or in other words, we can say that little d is equal to 9.5 times the distance for this single slit in the screen, big D. And we can box that in as our solution for part A. Okay. Part B wants us to do a similar action, but again, for part B, it says when the interference is at maxima, since we just did it for part A when the interference was at minima. So we'll start a new page here, part B. So that when the interference pattern is at maxima, we have the distance between the slits, d, times the sine of the angle theta is equal to, in this case, it's just m lambda. Whereas before it was m plus 1/2 lambda for a minimum. For a maximum, it's just m lambda. So now we can go ahead and again, as before, solve for the sine of the angle theta. Here again, m equals 9. So what we have here is sine of theta is equal to 9 times lambda over d. We have the exact same expression for the single slit diffraction, where we have big D times the sine of the angle theta is equal to m lambda. For the single slit diffraction, again, m is equal to 1, and we can plug 9 lambda over d into our expression and solve for little d. We find that little d, the distance between the two slits, is equal to 9 times big D, the distance between the slit and the screen for a single slit diffraction. And we can box that in as our solution for part B in the final part of our